So, couple quick announcements. Next week is reading week. Second part, I've been called away to Zurich on the week that we're supposed to go to our midterm. We have to move the midterm back 1 week. So the midterm 2 is going to be on March 24th. I will update all parts on Canvas. Check your calendars. If you do have some things, let me know. We can move it around at this point, but it will not be on the 17th anymore. We have 1 more week of time. So, second announcement 2. There is the Western Canadian Undergraduate Chemistry Conference coming up. This is being hosted here at UBC. It's a research fair being done by undergraduates. This is basically a summary of work that's being done through all of Western Canadian universities. If you'd like to participate, please go come and check this out. This is a really interesting example to get involved and see what else is going on at other campuses. There's also an open house in chemistry coming up. So the chemistry department will be having an open house in the next couple weeks. I will let you know what that day is. I may have to post it up onto Canvas. But if you want to do a rotation through the labs, see what's actually happening here, it's a good way to get involved or at least meet some other potential research faculty in chemistry as well. So last class, we talked about our carboxylic acid derivatives. We did our cleavage of our tertiary butyl esters. The T-butyl esters, remember, are different than the cleavages that we did before with our other nucleophilic substitutions. They clip towards the carbon group, not the oxygen carbon group to our carbonyl. Acid chloride preparation and our anhydride preparations is the parts that we worked through. So from here, what are the products of these two reactions? If we mix these two fragments together, what do we form? Okay. So in both of these reactions, we have an anionic nucleophile. And these are additions to what looks like acid chlorides. There's our leaving group. This is your traditional acid chloride. Notice there's something a little different about this one. You have an oxygen here. This is actually kind of more like a carbonate. But functionally, you've got this carbonyl acid chloride function. It's going to act in a similar way. So treat this in the same sort of addition profile that we have in the other. So in both cases, what we're doing is we've got our nucleophile, our oxygen, we've got our leaving group, in this case the chlorine in both cases, and we're going to add a new bond between the oxygen and the carbonyl. So in the first one, we've got our left-hand fragment. It's this oxygen. We're going to have a new bond to our acid chloride piece. The overall substitution here is replacing that part and giving us this anhydride. Remember, what do we call this? This isn't just a normal anhydride. This is called up at the top. Yeah, this is a mixed anhydride. Reason why is because the alkyl fragments on both halves are different. They're chemically non-equivalent. It means that those two carbonyls are both electrophilic. If we added something to this, adding to the purple carbonyl versus the green carbonyl would give you two different products. We're going to talk about how we impact those two things. This is why we use these mixed anhydrides in this productive way. In the bottom one, same nucleophile, new bond, but now to carbonyl, oxygen, and then this neopentyl part. Still like an anhydride. It's actually this anhydride, almost like a carbonate it's called. That's not important. But think of it as both cases. You have two different non-equivalent carbonyls. The green and purple are not the same in both cases. And again, the bottom one, electronics are a little bit different. Top one, sterics are a little bit different. You have this bulky group here versus having this oxygen here will help us to impact it. We're going to come back to how we use those later in the reaction today. So up until now, we've built up this kind of series of nucleophilic substitutions. We've introduced you to the conversions in between those. Acid chlorides now is our global reset. This is how we go from our carboxylic acids up to the most electrophilic systems, and we started to work down to our anhydrides and our amides. We're going to go through those. That's the practical part. The other thing we're going to touch on today is the actual experimental part, getting these reactions to work. Remember, if I do a reaction with an acid chloride, one of the things that happens is an acid chloride plus some, let's say, H nucleophile is going to give me HCl as a product and our final species. So the general reaction we're doing here from these acid chlorides, they're great electrophiles, but one of the consequences, if we go in with a neutral nucleophile, like an alcohol or an amine, you have one equivalent of HCl being generated. So we're going to talk ways of how we deal with this one beyond just a standard base. This is what we call our Schotten-Baumann reaction conditions. It's a procedural-based way of sort of dealing with things. And then we're also going to talk through anhydrides using mixed anhydride reactivity. So back to our general chart. Remember, top left-hand corner is where we're playing right now. These are the most electrophilic species, and they allow us to access anything down this sort of sequence. Going back up this takes special conditions, more energy. It's harder to get out of an amide once you form them. So we're going to talk specifically about getting into those more stable amide forms today. So the first one is, imagine you did a reaction where I'm using just a neutral amide and a neutral amine, and an acid chloride or an anhydride. You have a similar case. In both cases, I have a very good leaving group. Chloride here versus acetate as my leaving group constituent. So both cases, good leaving groups. In this case, if I'm going in with a neutral nucleophile, not the negatively charged species, the neutral nucleophile, notice that if I don't add any sacrificial base, anything else, I need to have two equivalents of the nitrogen species to make this reaction go to completion. The reason why is as this reaction runs, just as I mentioned the slide ago, going in with a neutral nucleophile means that that hydrogen, if you remember the mechanism, we're going through, we end up positively charged intermediate that's going to have to dump that positive charge somewhere. That's where you're generating one equivalent of an acid. So that HCl is going to be tied up with your nucleophile. So this is just a quick mention. If I cannot add, let's say, triethylamine or another sacrificial base, this is the consequence that you're going to be dealing with. Both the anhydrides and the acid chlorides produce this one excess equivalent where your nucleophile is playing two roles. It's both adding to your system to make your amide. It's also doing an acid-base reaction and getting tied up over here. So that's where this double nucleophile is necessary. That's only, again, obviously the way to get around it is we would add a sacrificial base so we don't have to waste extra nucleophile. So again, where does this come in? It only happens when we're dealing with these anhydrides, acid chlorides. These are the really, really good leaving groups. And when we're adding just a normal mild base to the system, a simple amine, which is also a protonated system. We're going in with a neutral system that's good enough to act as a nucleophile this reaction, but as a consequence, you're stripping off one proton as this reaction goes. You're producing a single equivalent of a strong acid. And to prevent that nitrogen from being protonated in this reaction, we have to have a base to sort of suck up that proton. So there's two ways around this. Like we said, the first one is if your amine is really cheap, plentiful, we just have to make sure that we go in with extra amine. Two equivalents over here are possible. We make the molecule of choice where the second equivalent is acting as that basic species. So that sometimes we can do this if it's a very cheap molecule, if there's some reason that we can't use triethylamine or something else, that is an acceptable way to do it. But again, why we're saying this is, remember, as the protons are formed, this is not a nucleophile anymore. Once we protonate it, it's out of the system, and that's why we have to have two equivalents, one to act as a nucleophile, one to act as our base. The other option is what we discussed last class. I can potentially run it with triethylamine and pyridine. So I can use something like triethylamine or pyridine to act as my base. Now, good side, it means I can focus on one equivalent of my amine, one equivalent of my acid chloride. Both the two fragments are coming together, acid chloride and amine, to make my amide. But why you might not deal with this, remember, the reaction's done. You're going to have all these other molecules which are our salts. These are water-soluble components, and there are some times that your amide that you're forming and your salts are inseparable. Getting them apart from each other is still a consequence you're going to have to deal with at the end of this. Or there may be a molecule that's sensitive to these acid chloride salts and stuff too. So you need sort of different optionality of how this reaction works. One other thing I wanted to quickly touch on as well too, question from last time about the acid chloride formation with thionyl chlorides. Why don't you use pyridine? I misspoke. What I was mentioning is you cannot use pyridine when you're using neat thionyl chloride. That was the mechanism I was showing you guys yesterday, is the very basic system of I can take an acid chloride, thionyl chloride, stick them together, I will get HCl and my acid chloride. Nothing else. It's just energetically driven on its own. You can do the full solution-based one where you have all those components and your sacrificial base. I'll show you guys that mechanism in the upcoming components. But I just wanted to touch on that part before, because this is where we're transitioning it over to the first theory and application. So the two examples I showed you on that last slide, if I have to run the reaction and I can't put in triethylamine, you're going to have to pay with 2 equivalents of your amine. That's your option 1. Option 2, I can use triethylamine or pyridine. That means I'm using acid chloride, my nucleophile, my amine, and my sacrificial base. Again, downside, I have to clean up those other components. This stuff here still needs to be pulled out of the reaction. I need some way to separate them. Your third option is to look something like this. This is more like option 2, but it's actually taking advantage of physical phase split. So you guys have done a separation in the lab before, liquid-liquid separation, right? You know that liquids can separate, so water will separate from oil in something like a SEP funnel. That binary separation, yes, it's very useful for working up reactions, but we can actually make use of it for doing chemistry too, because what we do is we almost set up like a cell. You know, an individual cell is like a bag of water with a lipid coating and then the exterior. Compartmentalizing things where some chemistry is inside and some chemistry is outside gives us an interesting handle to do things in this kind of more like a dynamic behavior. Think about it this way too, that I can actually set this up where if I had 2 phases, an organic phase and an aqueous phase, some of the molecules I'm running will be more partitioned. They'll dissolve better in the organic phase. Some will dissolve better in the aqueous phase. And if we look at the molecules we have here for this type of reaction, what they did, this is an originally earliest way for sort of doing peptide formations, is using this chemistry called the Schotten-Baumann chemistry, using an acid chloride, your amine, and this time I can use a really simple base like sodium carbonate. So sodium hydroxide or sodium bicarbonate. This is nice because my byproduct is CO2 and water. So this is a very clean reaction. I get away with only having to use 1 equivalent of my amine, 1 equivalent of my acid chloride, where the sacrificial base here is this inorganic material. So you're balancing a whole bunch of different properties. Number 1, I can do this because sodium carbonate, sodium hydroxide, will not dissolve in organic solvents. It's going to sit at the bottom. And what that means is if I'm running this chemistry, I can't really use it as an effective base. It falls as a solution. So I need to dissolve it in water. Well, that's great. I can take sodium carbonate, dissolve it in water. That problem's solved. But you have this molecule here. The amine can kind of go in both layers, right? It's a polar protic material. It might dissolve in the aqueous layer. It might dissolve in the organic layer. We can extract it. You guys have done pH-sensitive extractions where you can sort of push it and pull it between the 2 phases. What do you think happens with some molecule like an acid chloride if you try to dissolve it in water? Yeah, some people giggle. Is water a nucleophile? How did you make this acid chloride? You started with a carboxylic acid. You took thionyl chloride. You generated SO2, HCl to rip out that OH from the acid chloride, or the carboxylic acid, to install the chloride. You just spent a lot of time and effort and energy removing the carbonyl, the hydroxide from your carboxylic acid to make your acid chloride. You've pulled water out of the system. So you just made this material, which is this very electrophilic compound. This molecule, if you introduce it to water, will go off like a bomb, right? Because dissolving it in there, it's a very rapid reaction. Water is a very good nucleophile. If you try to dissolve it in water, you've got a ton of that nucleophile present. So on its own, acid chlorides are not compatible with water. It's like a Grignard. You cannot run a Grignard reaction in water because of the protons that are available here. But this is a really sneaky thing you can do. What we're doing here is I take an organic solvent like toluene, DCM, and the acid chloride hides in that organic solvent. The water isn't invited to the party. The water gets to sit over in a separate phase, and the base is hiding out in that phase. So what we just did is create two compartments. The carbonate hydroxide base is hiding in the water, the acid chloride is hiding in the organic phase, and this is where our amine acts as the social glue. Its job is to go between both layers and move protons between both layers. It's the shuttle. Remember, as you protonate an amine, it becomes positively charged. It can go into the aqueous phase. As it goes in the aqueous phase, it's going to go find the base. If it finds the base, it dumps a proton. And then it becomes neutral, which means it goes back to the organic phase. So it's walking back and forth between the two rooms. So this is an example of taking the chemistry you guys have seen, and now we're applying it back to what we would do in the lab and sort of the physics of it. We're running two different reactions in two different phases. So in the organic phase, let's say we have dichloromethane as our solvent. Because dichloromethane is very dense, it's the bottom layer in this particular mix. If we use dichloromethane, that's going to dissolve all our nonpolar material, such as the acid chloride and the neutral nitrogen component. When those two guys are hiding out in the organic phase, we're going to do our nucleophilic attack. That makes a zwitterionic compound where a second molecule of my amine is going to act as my base. I get my tetrahedral intermediate and a protonated form of my amine. So what's happened here is the second molecule, normally, if I just ran this in organic phase, I would need two equivalents of my amine. Temporarily, one molecule goes through. One amine is my nucleophile. A second amine acts as my proton scavenger. We're not done yet because we have this aqueous phase up here. Once it's protonated, it can now dissolve up into the water phase. Now that it's up in the water phase, it's like, cool, I'm nice and protonated, it's great. Oh, hey, there's sodium hydroxide up here. There's sodium carbonate up here. I can now get rid of my proton. I can be deprotonated by my base, and now I'm neutral again. Now that I'm neutral, I can go back into my organic phase, and I can go around again. Your catalytic base here is just this, basically, part of your amine. Its job is to pull protons off your intermediate, become protonated, go over to the aqueous phase, dump the proton to hydroxide or carbonate, become deprotonated, and then back into the organic phase again. So it's going through that cycle. The rest of the molecule, this fragment here, just completes its nucleophilic substitution. We collapse the tetrahedral intermediate, we get rid of the chloride. Nice thing there is chloride is also being extracted up into the aqueous phase. So this is a living system. This is a really unique way that this reaction can work. And again, what I find super cool about this is you're taking a molecule, the acid chloride, which is normally completely incompatible with your water, and just by dissolving it in grease, that both keeps it protected away from the water, because very much, most of the water can't get into the DCM anyway. Yes?
Are you able to do this reaction without shaking it and end up having water react with?
Very good question. Can you do this reaction without shaking it? What do you guys think? So your concern is like salad dressing, right? You've got two layers that are nicely separated. If you shake it, well, they're going to get mixed together. So in fact, when you do run this, you absolutely have to shake it, because if you don't, this transition here, think about it in the scale of the molecules. This molecule down here can't see that bilayer. It takes forever for it to find its way by diffusion to that phase. You have to agitate it to make sure that the mass transfer between the two phases is good. It's just like if you're doing an extraction. You can't pour your aqueous and organic layer for your workup and just go, do your thing. You've got to agitate it to get them to mix. The nice thing about this is this reactivity barrier, getting water to go inside the micelles, still loses compared to the protonated amine. So you're right. Shaking it will you do two things. You have to stir it in order for the reaction to actually work fast enough. Stirring it too hard in like a ninja blender, and yes, you will drive enough water in there that the acid chloride will detonate on you too. So you're kind of walking a line there. But most of the time, the nice thing is the solubility of the water kind of takes care of it. This is one of those cases that the physics works out perfectly where it works for certain solvents. What do you think would happen? So this is DCM and water, right? Toluene water works great too. This is another good example. If I did toluene water, where is my organic layer? So let's say that one more time. If this was toluene water, is the organic layer on the top or the bottom? Who says bottom? Who says top? Yeah, it's less dense than water. It will rise. So where it is, do not just look at this and go, oh yeah, reaction's happening at the bottom of the flask. No, look at the density of your organic materials. That will define where that is. Again, for anybody who's done extractions, if you've ever done that game of, I'm extracting with hexane, that's definitely the bottom layer, guys. Well, you just screwed up your lab for your partner, right? Like it's in the phase depending on where your densities are. So toluene works and DCM works. Do you think this works if I used methanol? What if I took methanol and water? Do I get a bilayer? No, so that will totally not work because you're dissolving everything. It's got to be something where you have salad dressing. Hexane water, toluene water, DCM water. What about, what's that? Diethyl ether. What do you think? It's not super great. You can do it. The problem with things like diethyl ether, remember, think back to your extractions. When you extract something with diethyl ether, what's the next thing you do after you've separated all your organic layers, but before you go to your rotavap, you probably grab some powder and do something? Sodium sulfate or magnesium sulfate. Why are you adding that? To get the water out of the ether. Ether dissolves a pretty good amount of water and will probably blow this up on you, right? So there is a balance here. But that's the chemistry that's happening, right? Again, this is one of those cases where you're using physics and chemistry to run this, and it's the very simplest version of like a small catalytic system. Yes? How do you know that toluene is less dense than water? Who's played with toluene? Okay, I will give it to you then. I'm sorry, this is one of those points where, well, what do you do on Wednesdays? Experience is one, right? But actually, if you just generally think about it, this is something you all have probably experienced. Water, density of 1, right? Almost all organic materials, density is less than 1. Everything else, light petroleum crudes, everything else, organics are usually under 1. DCM is your only guy which is heavier than water, pretty much. Chlorinated solvents are the things that are both nonpolar and more dense. Other than that, it's always organic on the top. Again, guideline, not a rule. There's ways of playing with that. So, if you run this over here, why is it important to add the acid chloride directly into the organic layer? If I'm doing this addition here where my DCM is in the bottom, usually you'll get a diagram like this where we're syringing in the acid chloride through the organic layer. Why does that make sense? What we just talked about, right? Yeah. Because if I just took it and dropped it in, this entire transition here, I'm asking for trouble, right? If you can directly add it to the organic layer, you help this whole process of mixing and co-mixing. So, again, this is a really cool reaction. I've run it a whole ton of times. If I had to separate these two layers, which layer contains my amide product? Again, based on the diagram you have over here, you're pouring it out of the bottom. Which is it? First layer or second layer? Okay. Everybody in one creepy voice. It is A or B? It is A. This bottom layer will be the first one to exit. The first layer you isolate will have your product. Otherwise, if it was toluene, it's the second layer. You drain off the aqueous layer, then your organic is the second component. So, that's the practical aspects of using our acid chlorides. Remember, awesome electrophiles. You can form them directly from carboxylic acids. Consequence, you're going to have a strong acid you have to deal with, and you either have to have a sacrificial base, extra amine, or use something like a Schotten-Baumann chemistry. Now we're going to talk about anhydrides. There are two primary ways to make anhydrides. The way nobody freaking does it, because that's not going to be practical. Again, as an aside, I didn't mention this explicitly last time. On the final, we had an anhydride forming reaction. No, do not suggest this to make your anhydride. Most of the time, like, it works fine for acetic acid like this. Almost any other molecule, where you put anything else interesting out here, that leads to dead molecule, right? Most things can't take that temperature. I'm just emphasizing how hard it is to directly strip water out of these systems. The condensation reaction is not favorable. So what we do is convert it to an acid chloride, take the sodium salt, because these are easy, right? I can do the acid chloride formation, that's step one. After I've made my acid chloride, I can take a carboxylic acid, any carboxylic acid I want, treat it with base to make the sodium carboxylate. Now I can bring the two pieces together. So it's a two-step process to create first your electrophile from a carboxylic acid and then the nucleophile from an acid-base reaction with a different carboxylic acid. Remember, if these two are different, we call this a mixed anhydride, which means that carbonyl and this carbonyl, blue and pink, have different reactivities and will produce different products, right? Because they're transferring, if you get nucleophilic substitution to the left or the right, you're going to get two different acylated products as a result of that. So the good news, again, anhydrides, they're a little bit easier to handle than acid chlorides. There's some chemistries that we want to use these in preference to acid chlorides. Sometimes acid chlorides are just way too crazy. Again, you guys are Friday before the break. You all have your friend that you do want to hang out today with, and then not again after that because they're just too much after that point, especially on a break week. Your acid chlorides are your hyperactive friends that they're okay to hang around with under very specific circumstances. The anhydrides are a much gentler electrophile. They have a lot of the same benefits as your acid chlorides. The problem with them is we have potentially transferring two different carbonyls. So if we have a symmetric group like this, your typical reaction will look like you see here. A nucleophile, an anhydride, and a sacrificial base. Once again, this is just like our acid chlorides. Because I'm adding, I've got, in this case, I can decompose it as, there's my electrophilic center. If I choose that as my electrophilic center, that's my leaving group. That means this is my nucleophile H. And a result of this overall transformation, that hydrogen and this group are coming out as an acid-base pair. We're producing a carboxylic acid from this, or at least a protonated system where we've got extra protons we have to deal with. So the overall mechanism of this reaction, we're going to start off with our neutral nucleophile, and I'm going to attack that group and pop it up. That makes our O-, O acetate, and OH on our nucleophile. We have our positive charge. So we get a zwitterionic intermediate. That intermediate, we could deprotonate it, so our molecule of pyridine, I'm just going to say PYR. That has a lone pair nitrogen. We're going to deprotonate to give us back an anionic intermediate. You could do a second proton transfer, as we mentioned last time, if you feel like drawing it that way. Where we add back to a neutral compound, I'm going to do it directly from here. Where what we have to do is bring this down and kick out our carboxylate. So the final product is going to be our carbonyl onto our alcohol. We've made an ester out of this system, and we have one equivalent of our leaving group, which is now our conjugate base, and we have pyridine, PYRH. It's protonated on the nitrogen. This is our acid-base salt. So this is possible as we go through this system here. Now, I want you guys to work through this. What would happen if you took a molecule like this, acetic anhydride, with excess of this, as much as you need? What happens to this system if you get to the following product? The other one, too, is we can switch out the nucleophile. Instead of using alcohols as our nucleophile, we can do the same thing with our amines. Neutral amines attacking anhydrides is the same mechanisms that we did for the alcohol. So that one we'll do in the class after as well. In this case, since we're not specifying an additional base, It means that we're going to be using this, probably 2 molecules, as both the nucleophile and as our base to make this reaction move forward, if we're not specifying that pyridine or some other base is present. So, last thing to talk about is this idea of mixed anhydrides. So, anhydrides are good. Again, they're a little bit more stable. You can use them with the same kind of fidelity or reactivity as an acid chloride. That's a plus. The downside, like we just highlighted back here, if I start off with this molecule, there's a thing we can refer to as sort of like carbon efficiency or process efficiency. If you look at that anhydride starting material, what I'm trying to do is I'm trying to make an ester. This is why I'm doing the chemistry. I'm only really using those 2 carbons. The rest of this molecule is going out in the garbage. So good side, anhydrides are reactive. They're almost as reactive as acid chlorides. They're a little bit easier to handle. The bad side is you produce a whole buttload of waste by doing this because you're taking 2 molecules of your acid, dimerizing them together, and then using one of them to throw away. Half the molecule ends up the molecule of interest, half of it gets chucked. So if that acid is something valuable, we don't want to do this. If I just spent 2 weeks making that carboxylic acid, the last thing I want to do is make a dimer anhydride and throw out half the thing I just spent 2 weeks making. So this is where what we can do is use what's called a mixed anhydride. In this way, what you're doing is, think of it as this part here is our payload, which makes this your leaving group. Now, in that molecule I just designated, I've got 2 carbonyls, but I've specified that the carbonyl on the left, that's the acylation fragment I'm going to be using, and I've said that by design, the one on the right is not going to be my acylating group. Why is that? Sterics. What you have here is a really bulky group, which means I could take a nucleophile and attack here. That's possible, but if I took the same nucleophile and attacked here, this one is going to be hindered. What we're doing is setting up a system where I have my carboxylic acid of interest, the one on the left, and I'm adding a bulky carboxylic acid, the one on the right, which allows me to differentiate between my 2 carbonyls. So that way, this part here becomes my obligate leaving group. It's a way of programming in reactivity, which allows me to target on one carboxylic acid and use the other one for only the purpose I want. In this case, it's this T-butyl one. It's called pivoyl, or pivolic acid is this T-butyl carbonyl group. Again, fun fact, but not useful. Yep.
Is hyperconjugation also a factor?
A little bit. What you've also got, yeah, that's a good point. You have hyperconjugation donating in, which is helping to reduce the delta plus. The big thing is sterics, though. Remember, the large bulky methyl group is going to help shield off that one. This is the other, on here on the other side. This is a case where this is my payload, making this my obligate leaving group. So now look at that system. Red carbonyl versus pink carbonyl. Why are these different from each other? It's not sterics in this case, right? There's an isopropyl group, but it's far enough away that that's not what's helping me. It's the same kind of strategy. We don't want to attack the red carbonyl. We do want to attack the purple carbonyl. Why? Exactly. If you guys remember when we talked about how electrophilic carbonyls are, we have a lone pair here, which can be resonance this way, which helps to shut down that carbonyl. Or I've got that same lone pair that can be resonance into this center. We also have another flanking one here. We have an extra set of pi electrons that can act in resonance donation to the carbonyl in the red one. Only one set of pi electrons pushing in on the blue, or the one on the left, the purple one, excuse me. So having these 2 flanking groups here, this is electronics, and this is steric. So these are your 2 useful mixed carbonyls. You can start from an acid chloride of either of those 2 systems. functionalize a carboxylic acid to get an anhydride, and these two are your two different mixed anhydrides, which we use for synthesis very often. So you'll see them repeated. Remember, look for that core functionality. On one side, what we have is we're using bulk, this large sort of carboxylic acid, versus the other one we're using electronics. So in these guys here, first one, if I added a nitrogen nucleophile to the first one, to that system, would I hit red or blue? Any Liverpool fans here? Okay. It's okay. I was in a bar in Liverpool. I did not know about this, and somebody grabbed me by my lapels and went, red or blue? And I said, I play hockey. That was the only right answer. Anyway, you're going to do a nucleophilic addition of an amine using triethylamine as a sacrificial base. Who wants to hit the red carbonyl? Who wants to hit the blue carbonyl? Okay, discuss and let's talk again. There was like divisions right there, people side by side. Okay. Let's talk. Red, blue. Are the reds just way more good at sort of like convincing other people? This is like, what's it called? Who Wants to Be a Millionaire? You poll the audience and then they poll you that way. Are you sure? Why might it not be the red? It is the red, by the way. It's fine. No, what's your argument for red? Sorry. Yeah, argument for red.
Why would be red?
Yes.
The fluorines are super electron withdrawing.
Okay.
So they're pulling the electron density away from the carbonyl and increasing the carbocation charge.
So you're saying delta plus versus delta plus, right? The electrophilicity of the red one is much greater because the trifluoro is pulling on that. Good argument. Why might it not be red? Because of which, sorry? Aromaticity, not much there. Sterics might be something. You could sort of say, look, I've got 3 fluorines versus that. But remember, how long is a carbon-fluorine bond? It's actually really, really, really tiny. Fluorine is a point charge. It's very small. This is 100% the red one. The red one definitely wins out. Electronics is that first one. So that's the center you're going to hit. Okay, next one. Green, purple. Oh, okay, so you're voting. Whole class. Who says green? Who says purple? Why purple? Sterics, yeah. Bulky. You've got something that looks like a crazy big group over here. So yeah, in the end, this one is sterically easier to get to. This one is blocked off, right? I used to describe this for people that took 123 from me. I have one sister. There are 3 brothers, all about my stature. We're the blocking group. We do not let her get dating very often. That took a long time. All right, good. So in the end, what about these two? Do you think these reactions are going to proceed? And what do you think the major product is going to be under mild conditions? If we mix these together, what's going to happen? Okay, first case, anhydride plus water. Do you get a reaction? Yes or no? Yes? Well, you got a new, okay, if I took an alcohol plus an anhydride, would I get a reaction? Water plus this, absolutely. That can attack. We do our little Tai Chi balance. You are going to get one equivalent of a carboxylic acid and one equivalent of the alcohol. We're splitting it down those 2 points, right? The addition of this oxygen here ends up providing that oxygen. Water ends up being split as H2O. That's where you have your 2 hydrogens and your OH. So water absolutely can add across this. What it just means is anhydrides, like acid chlorides, are water sensitive. They can go down in energy from that anhydride level to our carboxylic acid level. Totally fits. That comes back to our reactivity scale. You remember, acid chloride's in the top corner. Anhydride's next down. Carboxylic acid's below this. This is all we're reinforcing here is I can put the 2 pieces together to make products that on our energy scale sits at that sort of number 3. You came from number 2. What about this bottom one? Reaction? Why not? Yeah, it's kind of like you can do that same game. It's like, well, let's pretend it works. If I did this, let's say minus, right, and then I attack the other one, I would make this. If I'm drawing 2 species, again, this would be the mechanistic outcome. If I took my Cl minus and did this addition, this is what I would form. If you look at your 2 products, those are our rapid way of making anhydrides. If I take an acid chloride and a carboxylate, wham, they're going to form on this side very easily. So that is not a productive reaction. This is going uphill in energy. We need something special to do this. Okay, I have one final thing to deal with, which is the giant bag of candy. Hold on, I got to go check Piazza. So, as voted by over, wow, that was pretty good. We had 132 votes. Coming in number 3 is the non-polar bears. Okay. You're going to have to, can you catch? Yeah. Don't make me, again, you said yes, I have it on tape. Okay, you can catch, I can't throw. All right, number 2 is the Whittle-Wittigs. Good job. I'm not doing that again. There you go. Number 1, by a large margin. When in doubt, epoxide out.
Okay, for this problem, we are adding a sugar. In this case, this is actually glucose to acetic anhydride, and we're using a large excess of it with a sacrificial base. In this case, we're using pyridine to help with our proton shuttling. We're asked to find the major product of this reaction. Now, previously in the class, we said that some alcohol can act as a nucleophile. Under these conditions, we're going to do our overall transformation, where the leaving group, in this case, if we attack that carbonyl, will be this acetate fragment, where we're using pyridine as our proton shuttle to move protons around as necessary. In this case, any alcohol can be attacked. Now, you might imagine, let's say a primary alcohol might be attacked quicker, but in the case of having excess of this reagent, this is actually a standard way of doing what's called a protection of a sugar for other standard chemistry. So the product here will be our carbon skeleton, like this. And each of the acetates will be converted, or each of the alcohols, excuse me, will be converted to an ester in this case. So that includes each of the ones exposed. Here, again, here, we will have one more here and there, and also, that will also include our the acetal-like center. So remember, this is a hemiacetal. Under these conditions, we will actually per-acetylate it in each of the fragments over here. Now, we might imagine this one is a little bit more fragile. It's a little easier to displace with, let's say, water, right? That center might allow that center to open up because we now have attached this as a decent leaving group. But under these conditions, every OH that you see will be converted into a ester. Now, for this one, we're asked to practice the mechanism. The mechanism is actually drawn out on the previous slides, or just the next slides over here, seeing this one. I'm still going to go through it step by step just to help to highlight that if it's necessary. So first of all, we've got two carbonyls. In this case, this is symmetric molecule where both of the R groups is the same. However, mechanism persists no matter how we do our nucleophilic attack to our anhydride. I'm going to use, let's say, this center here. So that'll be our first addition. That's going to get, and I'm just going to designate them with a different color. So we're using this center here as our carbonyl we're doing the nucleophilic addition to. We just brought in the amine. And the blue one is going to end up becoming our leaving group eventually, and we still have a positive charge over here. Now, under these reaction conditions, you can imagine that we still have, at least we're not given any extra exogenous space, so in that case, the amine itself will act as our basic species, so we'll probably do a proton transfer to give us the next intermediate. You can see what we just did here is we've now neutralized the nitrogen. And you can think about that. One of the main reasons we want to do that is to allow the mechanism to move forward. What we're going to be doing is we want to actually eliminate this leaving group. Right now, if we leave this one positively charged and we're to bring this charge down, it's most likely that would be our leaving group. Now that we've done this, and we've now made the center neutral, we've set it up such that when this tetrahedral intermediate collapses, we're most likely going to eliminate the better leaving group, in this case the acetate, rather than the amine. So under that fragment, that's going to give us our acetate leaving group, and our now amide here, like that.